let's continue. We stay with Florian. Next speaker is Florian Gerlich from Insolight, working as part of the HIPERION project. Florian is a co-founder and was the COO and is now a design architect of Insolight, and he will let us know more details about Insolight's innovative hybrid PV modules with efficiencies larger than 30%. Florian, the floor is yours.
Thank you very much. I'll share my screen when I can. So, thank you for being here and listening. So I will present the technology that is being promoted within the HIPERION project. It is really all about high efficiency and how we can bring high efficiency modules to market, how to manufacture them, and how to move forward in improving the efficiency. So I made a quick agenda. So a quick introduction about the HIPERION project, technology overview. I'll likely spend most of my time in this part as it seems to be most interesting given the previous talks. Quickly addressing the challenges and breakthroughs, what has been made during this HIPERION project. I'll just show one or two because I know that other HIPERION talks are taking place in the coming days as well. A status and a look ahead, basically how we move forward, what is needed to move forward. So the HIPERION project is quite a big one, and at least for me, with 16 partners all across Europe with a total budget of 13.5 million euros. You see some of the partners here, which are quite diverse. We have research centers, we have industrial companies, and us here bringing in the technology. So it is really about not only developing something in the lab, but really how can we bring it to market? How can we manufacture it at scale? This is among the main questions that we try to answer here. So in terms of technology overview, a couple of years back when we started Insolight, I don't know if you're seeing this small thing. I'll try to get rid of it a little bit. A couple of years back when we started Insolight, we looked at what exists in the PV market, and there's on the one side the conventional PV or standard PV as we usually call it, which most of you are familiar with, which is very simple, very reliable. It's being produced in massive quantities all around the world, but with limited efficiency still. I know there's work being done in order to improve it, which is our talk a couple of minutes ago of how we can go to 24–25% of efficiency with these technologies, but unfortunately they're not massively spread on the market yet. On the other hand side, you have the concentrated PV, a field that has grown quite a bit 10 years ago, or maybe 15 years ago. It had a lot of attention, but the issue we see, and from what I see the market also has seen, is that it doesn't fit in the right context. You get very high efficiency, you get a lot of energy per square meter, but it's very difficult to mount a dual axis tracker on a rooftop where it's actually needed, or an industrial complex where it's actually needed. And so what we try to do here at Insolight is to integrate those two technologies, to take the high efficiency from the concentrated PV and take the ease of mounting and the ease of the ease of mounting of a traditional solar panels, which means that we actually integrate the tracking mechanism inside of the module. This is really what we as Insolight have developed, and what we as HIPERION are trying to where we try to scale up the production and bring it to market in a good way. So this is these 29%. I don't know if you can see my mouse, but I'll quickly go to the laser pointer. So these 29%, they were certified by UPM in Madrid a couple of years ago. You see the upward trend, and we're also trending upward here. So we've crossed the 30% mark with the latest modules that we've built. And the goal now is to build them in a repetitive way, and that's really the key now. So the idea here is to be ready for mass manufacturing and to be compatible with standard mounting. And the idea of high efficiency is that in your balance of system costs, a lot of cost goes into the mounting, into the installer, into transport, labor, and so on, whereas the solar module itself represents a fairly small part of the cost of the whole installation. And so we believe that the way we see it is that even if you increase the price of the module a little bit, if you increase the performance enough, you gain on the overall system cost. So this is a slide just to explain how it works. I'll spend a little bit of time here. As alluded to earlier, it is in the end a CPV module, but with integrated tracking. So you no longer need an external tracker or a dual axis tracker in order to make it work. These are mounted just as any other solar module on a rooftop or on a whatever, wherever you mount solar modules actually. And so we try to kind of stay out of the clean room. We try to use technologies, be it solar cells or other things that already exist on the market, instead of reinventing the wheel on this side, and try to integrate it to be a better architect, to say, in putting pieces together. So we have two layers. First, an optical layer. It's kind of a honeycomb array of lenses. And as you see here below, the direct light is being concentrated onto tiny solar cells. So these are roughly 1 square millimeter in size. So you can already guess that if this is, for example, 1 square meter or 1.6 square meter, you will have thousands of solar cells and thousands of lenses to be assembled. And this is part of the big challenge here for us to make it reliable and repetitive, is in order to assemble it in a repetitive way, in a precise way. So the way it works is you have these two layers. The first layer that concentrates the direct sunlight from the sun and focusing it on these tiny solar cells. And this bottom layer, so the whole layer where the solar cells are mounted, this can move in 2 dimensions. As the sun in the sky, I mean, relative to Earth, is moving in 2 directions, left to right and up and down a little bit, depending on the seasons. We also need to have 2 degrees of freedom in our module. And so this is how we achieve this. It's really the 2 layers moving one relative to the other one. Furthermore, what we have really integrated with this HIPERION project is the integration of diffuse light gathering. So you have a layer of secondary cells, which you see here. So if on the bottom left, you see again this lens layer that's being built separately from the backplane. So the backplane is what is typically the cells layer. And so we have a mixture between standard solar cells, so standard wafers that you simply laminate together as you would do in any other solar panel, superimposed with high efficiency solar cells. So this is what you see here on the right side, really, is that I'll start with the bottom image, where you see there's still our first generation product with these white traces, which is basically a PCB on glass. So you usually see PCBs as green FR4 plates. Here, instead of going with FR4 as it's not transparent, we went with glass. And so we printed a circuit board, placed all the solar cells on it, and laminated this together with a standard solar panel. On the top here, you can see one of what I think is quite a nice image. You see this laminated backplane that's being tested, making sure that each and every solar cell is being illuminated. This is one of the other challenges we have, is reliability, making sure that we are reliable, that we can last for these 20, 25, and maybe even 30 years that a standard solar panel is being warranted for. And on the bottom left here, you see that these 2 layers are really integrated with a standard solar panel frame. Here we still are at 45 millimeters. We're looking into making this thinner. But there is a certain thickness to this technology, given that you have these 2 layers. So here, this gathering of the diffuse light is really what enables you to also reliably push above the 30%, because on one side, we often get this question of reliability, and you can see this module as a standard solar module with a boost on top of it, meaning that if for whatever reason the CPV part stops working, you would still have a standard solar panel below that gathers light a little bit less, obviously, because you have some shading with the traces here. But the secondary layer really plays a key part in achieving the high efficiency year-round as well. Given typically in Switzerland, we've got 50% of the days in the year which are cloudy, and so CPV doesn't work very well when it's cloudy or when there's diffuse light, and this is where the secondary layer really comes into play and plays a big role in in producing energy. I talked about the first layer, so these optics. So we're one of the key things with our optical layer is that we can not only concentrate the light when it's coming straight down on a module, but we are also able to concentrate light when it's coming from other angles of incidence. We're able to concentrate light up to 60 degrees, I mean plus minus 60 degrees, so from the morning to the afternoon. Winter and summer, it obviously depends on what kind of tilt you mount your module with. But here on the left, as I mentioned before, where a lot of effort is going into manufacturing. How can we manufacture this in a reliable and repetitive way? Here on the left, you see an attempt of a jig, how to place these lenses precisely, how to glue them, how to dispense glue in a good way, in a repetitive way, in a reliable way as well. And on the top right, you see one of our layers of glass that's just been glued. And so these 2 points, I'll just jump back to the previous slide. So these 2 points, on one side, the back plane with all these cells that needs to be aligned with the front plane, what we call front plane, or the optical plane. Each lens has a cell, or each cell has a lens, whatever way you want to look at it. And it's really about a matter of precision tolerance and how can we align those two layers precisely together, and how throughout the day we can move them in a reliable way and precise way in order to produce this peak energy. So a couple of images here of a pilot site here on the left, and a couple of modules on a test stand on the right. So what you see here on the right, on the bottom image, you see this dual, these standard solar cells on the bottom that are gathering diffuse light. On this day, I mean, you see it was quite sunny, so the test here really was to see how well the primary cells or the CPV cells are working, but nevertheless not neglecting the secondary cells. We sometimes purposefully during testing misalign the module to test how these focal spots affect the secondary cells in order to make sure that there's no issues with this in case anything were to fail. And on the left side, you see a couple of modules installed at our pilot site here at Insolight in Switzerland. We've got a pilot site also at Fraunhofer ESA in Germany. We've got some also installed at UPM in Madrid. So the first part of the HIPERION project is really about developing the technology, making it, basically scaling it up mostly in terms of manufacturability and testing it in various climates. And the second part of the HIPERION project, so the next 2 years roughly, will be dedicated to manufacturing more modules and installing them with other partners at various sites throughout the world, not only research institutes, but also utilities and companies that are more focused on the deployment of solar modules rather than the research of solar modules. So a couple of challenges and breakthrough. Nothing is easy, obviously, and I also already alluded to the fact that precision is what is really key for us. And one of the nice breakthroughs we had is here in the bottom. I don't know if you can see it, but this is basically one big piece of glass with the printed layout on top of it, with all the solar cells stored on top of it. So you should really think of it as a massive PCB. It's in this case a 0.6 square meter PCB, so it's not yet full size 1.6 square meter, but we're getting there. And this has brought us immense. It has made manufacturing so much easier by having only one large piece of glass in the back instead of needing to assemble this by hand or so. And this has also brought some better precision and reliability to having it all in one go. On the top layer, you see the lenses again. And as said previously, one of the big questions we tried to answer is how can we manufacture this in a reliable way, in a repetitive way? This is among the most important things. It's fairly easy, in my opinion, to build something that's very good one time or two times. It's very hard to build it with machines and do it tens of times, hundreds of times, or even thousands of times. And so some design choices were made in order to facilitate manufacturing, and some design choices were made to facilitate performance or to improve performance. And this was a constant battle among the partners. We all try to obviously bring the project forward. But at the same time, we all have different tasks. We all have different deliverables to deliver. And so it's been a challenge, but it's been a really interesting challenge to also listen to what other companies or research institutes have going through their mind and how they think and how it can bring us forward as well.
1 minute.
1 minute? Okay. So far, we've built 50 more modules that have been built and are operating. The oldest is just over 1 year old. Individual modules have reached 30% efficiency. Now, here I say individual modules, coming back to what I said previously, we need this to be more repetitive, and we have this Gen 2. So all the 50 modules here are what we call Gen 1, and Gen 2 is the second wave of modules that is being built starting this summer. And where we want really this repetitiveness and all the learnings that we've gained from the Gen 1 modules to be implemented. Looking ahead, scale is really everything. If you build 5 modules, it's going to be really expensive. If you build 1,000 modules, it's going to be cheaper. But I think what the solar industry has taught us in the last 10 years is that by ramping up volumes, you can really drive down costs quite incredibly. And the second point, the market entry is really focused in locations where you have limited area and where you need high efficiency. Again, if you go to the desert, the square meter is, well, cheap or even free. But if you're on a apartment complex where you have, I don't know, 10-story buildings, 20-story buildings, the roof area always stays the same, but you've got more and more people living in it. And so it's really where energy density is required. 30% efficiency really makes sense, even maybe at the detriment of cost sometimes. But we see in certain regions of Europe where buildings are mandated to be energy neutral. So standard solar panels sometimes no longer make sense, and do not answer the law sometimes. So yeah. Can you come
to conclusions? I think
yes, and that was actually it. I don't know what conclusions I have. I'd be open. Well, I guess there's some questions in the chat already. I see a small pop-up up there on my window. So yeah, that's how we try to go, or we are going to 30%, and what is left to do is really make it really repeatable.
Okay, thanks, Florian. Indeed, there are already some questions. It would be nice if you could answer them. I think there will be also some follow-up questions because your technology is really different than most of the others out there.
Quite. Yeah.
Okay.
All right, I'll head to the chat. Thank you.
Thank you. Okay, then let's